Deborah, you're good to start the session.
So good afternoon, everybody, and welcome to this session focusing on applications of metamaterials in the built environment and construction. I think just as way of an introduction to the sector, I think we all see that there has continued to be challenging times for the materials industry who supply construction, huge fluctuations in global demand, creating the need for resource supply, coupled with high expectations from asset owners, end users and surrounding community in performance, as well as affordability. And that means different things in different parts of the world. So if ever there was a time for increased choice, optimized processing and installation, and also retaining materials value, it's now. However, with any change comes risk and upfront costs to validate and standardize. So also to ensure efficient application with optimized performance for new materials and technologies, the skills for those who design, build and also maintain the assets which utilize them in the built environment also need to be fit for purpose. Whilst there has been a shift back towards natural materials, there is still a critical place for synthetic systems, providing they're used in an efficient and sustainable way. Metamaterials are an example of this, and as a broad classification have been developing and exploited for over 20 years, so they're not new in that sense. So our four speakers today will explain what particular metamaterials that they use or develop in their business, how they provide their unique and often superior acoustic properties when used in the right way. They will also describe how these benefits are being realised in a growing range of applications, also at increasing scale. So without further ado, we'll move on to the main speakers. If I can ask you to, any specific questions that you might have as you listen to the presentations, please put them into your chat area. We are actually going to run through the four presentations one after another, and then I'll shepherd the questions to appropriate speakers in the Q&A afterwards. So without further ado, I'd like to introduce our first speaker, Gianluca Memoli, who's the founder and CEO of Metasonixx. Gianluca.
Thanks, Deborah, and thanks for giving me the chance to tell you something about Metasonixx and what we do. So I decided to tell you a story about a recent project that we completed last year, some work in hospitals, and the story starts in, sorry, first let me share sound so that you're able to hear something about what I'm talking about. So the story starts at the start of 2020. At the start of 2020 we were exploring, so Metasonixx is a startup from Bristol and Sussex, and we were exploring ways of delivering sound in new precise methods inspired by light. So we had beam splitters where the driver and the passenger hear different sounds. We had telescopes where you deliver sound just like a small ball that moves with you. We had lambda plates, we had holograms where the sound takes a shape which might be complex. And we had already realized that actually if Metamaterials give control, then what we wanted as a company was to give control to the people who are not, whose needs in terms of acoustics management are not covered by legislation. But still, especially if they are affected by noise at work or at the office, they have an impact, a negative impact on their well-being. And then lockdown arrived. Now, you might remember those evenings when we were out on the front door. I remember being there with my kids and doing noise for the people who were fighting the start of a war, which is still ongoing against the virus. And we realized this changed us. We realized that we wanted to do something now. We wanted to do actually to help. We wanted to be part of the war. We wanted to, instead of actually giving noise to hospitals, we want to give them the benefit of silence if we could. And so what we did is we spoke with KTN, and whenever you have an idea, that's the best people to talk to. And they encouraged us to submit a proposal to Innovate UK. And the story I'm telling you about is what came out of that. So hospitals are noisy places, even if the recommended levels are very low. Low in the sense that the levels in dBs, so dB is or decibel is the scale that you use to measure, is a non-linear scale that you use to measure and compare noises or sounds. And you see 35 dBs on day is equivalent to the sound or the environment in a library where there is only the occasional shh. And if there are too many shh, then you move to a small theater or a large conference room. Now, if you have spent time in hospital, you know that that's not the reality. And in fact, a lot of studies has shown that actually the levels are much higher than that. And so there is a review here which was summarizes the studies made between 2015 and 2021, and says that actually the levels go as high as shouting at 1 meter away, or even sometimes as a rock band. My small contribution to that was a study that I did in 2014 in 2 London hospitals. So I was aware that that was an issue, and so it was one night while I was clapping that I went in and I phoned the clinicians I was talking to, first because I wanted to re-establish a link with these people who were fighting for us, but also because I wanted to know what had changed. And they told me it's even worse. Why it's worse? Because this is the noise of a standard ventilator. Now, I hope you can hear it. What you can hear is a small noise which can be similar to your air conditioning. And then at some point, there is an additional noise. And there are also alarms. Now imagine having that all the time, and imagine having a lot of those ventilators in a row. You can barely hear my voice talking. And if you'd add to that a CPAP machine or something with an alarm, as I was saying, then this becomes unbearable. So if you estimate, if you measure the noise made by a ventilator at the patient head, then and you estimate 10 ventilators in a standard COVID ward, or like the wards which were transformed into COVID wards at the start because we were to cope with the issues that we were unprepared. You get levels which are similar to what you get along the M25 motorway, both at day and night. So imagine working in a place like that all the time, and this has an impact both on patients, because obviously they cannot sleep well. It has a proven impact on the increased heart rate and blood pressure, and also this affects a delayed recovery. But it has also an impact on staff. So what you see here is the result of a study, of a survey made by the Parliament, by the Special Committee of the Parliament on the burnout of NHS staff. And you can see that clearly 2021 was a difficult year. But the interesting bit, if you compare those numbers, is that the word noise starts appearing more and more. Now, the fact that noise is something that you really don't want during the treatment of the sick is something that apparently has been known for a long time. There is this sentence which has been allegedly attributed to Florence Nightingale in 1959, and she says that is noise, unnecessary noise, the most cruel abuse of care. Now, without talking, without some noises, you cannot save lives, and so this is absolutely paramount. So what we thought is, can we do something about it? So this is the acoustic requirements for, imagine that you want to actually silence the ventilator at the patient's bed. So when during this period, since March 2020, I managed to go to the hospitals every time there was a low in the peaks. And so I managed to talk to the hospitals, to the nurses, and some of the and to take measurements, to test our panels and to see what we could make for those environments. Now, this is the spectrum of a ventilator normalized, and you can see that there is noise which is about flat, increases a bit as you go lower in frequencies, and then there are peaks which are the alarms. So if you imagine to sort out this, you can do that with a classical solution. You can put an absorbing material in between. You can put a very heavy piece of material between the ventilator and the patient. The problem is that this is not clinically doable, because anything that you put between the patient and the instruments need to be removed as quickly as you can, because you need to access the patient if needed. Also, that was a very important point. They wanted something which would not make the patient feel like being in a coffin. And so they wanted something which was ideally transparent. And then the last requirement was that it was cleanable as quickly as possible and as light as possible, because then they wouldn't need to, the nurses wouldn't need to call special people to manage those. So Metamaterials, we thought, can do this. So for us, when I talk about Metamaterials at Metasonixx, I talk about Sonoblind Panels, and these are panels which start from standard materials, or poor materials you could call them, so wood, plastic, metal, paper in some cases. And then you add a bit of the patented IP and you get objects which either cancel noise or manipulate sound. So we devised in this project 3 types of panels. One of them is a panel which lets a lot of air through and is very, very effective on specific frequencies. So imagine that tuned to the alarms. And believe it or not, there are some key frequencies which work for this type of instruments. So for those, we didn't look at transparency because we imagined them around the ventilator. These are very light because, as you can see here, most of the space is empty, and the physics which allow this to cancel out the sound is that actually the sound which goes through this and the sound which goes through this in a checkerboard interact on the other side and cancel out. Then we took the idea of making something transparent, and also that allowed air through. Remember the requirements, not in a coffin. And so we designed panels which allowed a bit of air through and were more wideband, so more appropriate for the type of noises that you want to silence from one bed to the other, and also in terms of acoustic comfort. However, they are much heavier in terms of weight. And this brought us to design a third type of panel, which instead has no air through, but is semi-transparent, and is also closed on one side. Now, strangely enough, this was the one that we imagined that as on movable screens or on wheels, just like a lot of the equipment that you find in hospitals, so that you can move it around very quickly. And if the weight is allowed, you can do it with a finger. So, and this was the first type of panels that I went to measure the first time in December 2020, and then again the next time I was allowed in the hospital was late spring, well, after May actually, in 2021. And this was the one selected for the first attempts in a word. So what we did then is, first we need to characterize it. Now, this is the type of panel as it looks like. The problem is that there is no standard way to characterize this object. I said that already in my previous talk, in the past section. There is a simple way that works for all the metamaterials, just like some time ago it was not easy to characterize composites. So we use 2 techniques from the literature, so used by others. And because of the tests that we did in Windows, we knew that this one here, the pulse scan, was actually traceable to an ISO standard. So we did the steps that you normally do when you try to assess whether your measurements are comparable with the method that everyone else uses. When you have a new material and you have to give an answer, yes, but how does it compare what is out there? So what you see here is the result of one of those type of measurements, and you see that there are curves in gray, which are microphone scans. There are the curve in red, which is simulations, and the curve in blue, which is the, let me call it, the benchmarked method. And for comparison, I also put a yellow line, which is a material which I called artboard, which has the same density as the metamaterial. So what you see basically between the difference between the yellow and the rest is the effect of the metamaterial. You can see that there are some frequencies. Remember, we wanted to silence the alarms, right? Here, there are some frequencies where it works much better than others, and then we wanted to silence the air flow. And then there are frequencies where allegedly it works much worse. Now, actually, when you go and test that, you don't find this dip in other methods. So there is still an open question of what happens here at high frequency, because at high frequency it's mass which dominates. But the key point is that we managed to, with 1 inch thick panel with no air through, we managed to get better than artboard of the same density. So to get the same effect, I need to multiply by 3 the weight of artboard. So standardization is needed as a key point in my experience in the past 18 months. So we made them and we put them in a panel. Now the requirement of them to be washable by a wipe, at the start we decided, okay, let's forget the transparency and let's just put something, a fabric on top. So there is fabric on this side, on the other side, and what we did is we took the panel and brought it in a ward which had been arranged for a COVID patient in a moment where another ward was used, so they were rotated. So we put the microphone down here where the patient's head would be, and then we put the panel in different positions. Now, when you see a place like that, that is the nightmare for an acoustician, because there are reflections all over the place. So you never expect that your panel would actually have an effect. And instead, it did. And we measured, in fact, 12 dBs in an environment where there are frequencies all over the place which do not, which pass through, which bounce and reach the patient in different ways. But also remember that we tailored this one to a ventilator, and in fact it worked very well with the ventilator. It didn't work so well with the CPAP machine, and the reason for that is that the CPAP machine has a lower frequency component in its sound, so it needs to be improved at lower frequencies. So what we did since then is, okay, we talked with the clinicians, we agreed next round that we go in the hospitals will be later on in March, probably end of February actually. And we also tried to improve the low frequency component. And to do that, I want to show you a comparison with the standard building material, which is Rockwool. So I compared the performance of our panels with a 50 millimeters panel of Rockwool. Remember, the weight is 3 times as much for Rockwool. And so what you see is that as you change the thickness of our materials by 10 millimeters here, you get response at low frequencies that are not there for Rockwool. So this shows a trend, and so there are then geometries which can increase this type of solutions and perform better at low frequencies. Now, this is the fact that metamaterials are tunable is one of their strengths, and I imagine that Daniel will show us something in that direction, because he has a line of panels which are specific for low frequencies down here. But the key point is that when we are using Rockwool, when we are using wool in general, maybe there is an opportunity for metamaterials to take over. Right, I want to finish with this video here, which summarized for us the project, and I hope you'll be able to hear the audio.
Intensive care units are noisy places with alarms and machinery all around. The pandemic has made hospitals into even noisier places, with negative effects on both patients and staff. Traditional technologies cannot help. They are bulky and difficult to manage. In this project, Team Metasonics used acoustic metamaterials to solve this problem. We designed panels that weigh 3 or 4 times less than traditional ones and can be removed when necessary. Some panels can even let light and air through. Next, applications expected in air conditioning, automotive, open offices and people's homes.
So at the end of any presentation, I would like to thank you for your patience in listening to me, and also I would like to thank all the organizations that helped me to reach to this point, and these are the universities which co-funded or helped us to found Metasonixx, but also the EPSSC and the Innovate UK, and all the advisors that have given us precious advice to go on. Thanks for your time.
That's great. Thank you very much, Gianluca. So without further ado, I'll hand over to Daniel Elford, who, excuse me, is Chief Technology Officer and co-founder of Sonobex Limited.
Thank you, Deborah, for the introduction there. Yeah, my name is Daniel Elford. I'm Chief Technology Officer for a company called Sonobex Limited. And we were a spin-out from Loughborough University, specialising in the commercialisation of acoustic metamaterial technologies. We like to use innovative, disruptive technologies to solve really big global noise problems. We are now part of a larger group of companies called Murford Group. They're based in the Netherlands, and we've been operating for over 65 years as a group company. And they've been around since the very first noise legislation was introduced in the UK. So we're very well versed of delivering standard noise control solutions. The sort of inquiries we've been getting very recently are applications where you need to mitigate noise, but still allowed airflow for passive ventilation or for cooling for different types of machineries. These are some of our standard old projects, which are chiller units on top of rooftops. And the only available solution beforehand was a type of acoustic screen type solution here. More and more inquiries are coming in now for ventilated facades or louvered sections of buildings to provide passive ventilation, but these have an inherent problem of leaking out low frequency noise. So you're always fighting a competing issue of airflow against acoustics here. More and more in the commercial and residential space, we're putting more ventilation products into people's houses and buildings. But again, there's an issue of low frequency noise becoming dominant because conventional type solutions work much better at high frequencies than low frequencies. And this is a project we delivered last year through Murford again, which is a ventilated loggia on the side of a building. But again, low frequency noise is not as mitigated as the higher frequencies. So what we're seeing is a big problem with low frequency noise. So what we developed at Sonobex is a new product called Noise Trap Blocks, which is a metamaterial based solution, but we wanted to allow passive ventilation for airflow for cooling and natural ventilation of buildings, but obviously focusing on improving that low frequency performance, where the standard type of solutions in acoustic louver or silencer, they don't really work very well at low frequencies. The goal to develop this product was also so it was modular, so it could be assembled by hand on top of rooftops for chiller units, for example. And a metamaterial has the benefits of being lightweight because it's not based on the mass law, which conventional acoustic solutions are based on. So that's what we did. We came up with a modular noise trap block solution. We fully lab tested this now, and we have enhanced low frequency performance compared to the conventional type solutions. Like I said, it uses a metamaterial based design. What it actually is a closely coupled resonator array that allows passive ventilation, maintains that lightweight ability to being able to be installed on rooftops. And we've also developed this product so it can be rapidly injection molded, create flexible designs. So we can now create screens, barriers, enclosures, as well as the standard louver type acoustic solutions in the market. And there's some nice pictures of our systems. Like I say, it's an injection molded plastic solution with no acoustic material contained within to mitigate low frequency performance whilst providing passive ventilation. We've fully tested this. Like I say, this is independent test results here, and we get superior low frequency. We like to focus on around 100 Hertz at Sonobex because that's a typical power transformer low noise problem that's experienced in the market. And we actually achieve a level of over 20 decibels at 100 Hertz, which far exceeds the performance of a standard louver. But what is important as well, we still maintain that high frequency acoustic performance as well as enhancing the low frequency performance. So I just want to put this in a bit of perspective. So our new noise trap blocks products on the left here, and our standard conventional solution, which was an acoustic louver, we call it the AKR 300, is on the right there. And things I want to highlight is the acoustic performance at 125 Hertz, we get 18 decibels in that full octave band, where the conventional standard solution only gets around 5 decibels. The overall performance of the RW value is pretty much comparable because we boost the low frequencies there. And we also have a better airflow requirement than conventional louvers, which infers a lower pressure drop value. So you have a better airflow for a certain open area in terms of this product. With the same thickness or depth of the solution, we are actually half the weight and actually half the cost with significant low frequency acoustic performance and equivalent overall performance. And to put it into perspective, the 300mm deep noise trap blocks is an equivalent to a 2.1 meter long passive, a parallel baffle silencer, which is another standard solution you get in the market. So one market we've really focused on this is where you need airflow and low frequency in commercial and residential applications. And there's been a lot of news recently about the heat pump and chiller markets. And by the end of 2030, around 60% of the world's population will actually live in cities. And in the UK, they are actually really pushing heat pump technologies to provide heating for your houses, for example. And there's over 25 million households purchase a heat pump in 2020. And that market is ever growing. But because people live very close to each other, as soon as you install a heat pump outside your house, you do get an increase in noise complaints here. And 15% of all UK properties have no outside space. So you then have to mount them on the side of your building, usually outside your bedroom window, which causes noise issues. And a heat pump is generally quite loud if it's very close to your window as well. And if all of your neighbours have these, those noise levels increase because there are multiple units installed on the side of a building there. The main sources of noise from a heat pump are the compressor, which is low frequency noise, and also the fan contained within it, which is more broadband noise. It's more easier to mitigate that higher frequency fan noise. And you have a tonal penalty that can be applied because of that low frequency tones generated by the compressor. And because a heat pump is an intermittent noise source as well, you can actually get a further penalty of a 3 decibel applied to certain frequencies, which makes that problem even worse. And the current state of the art in the market prior to Metamaterials was make silencers, make louvers bigger, longer, to have more mass in the way to mitigate those low frequencies. But that inherently creates a new problem with planning. You can't really install over a certain height on a rooftop if there's visual line of sight to a chiller unit, for example, up there. So what we've done at Murford Group, this is a standard conventional louvered product. It's a growing market, like I say, to mitigate heat pump noise. But these type of solutions didn't really work at low frequency. And we found this out during a number of installations of these type of products, a standard louvered product to provide airflow whilst mitigating some of the mid to high frequencies. We have a number of solutions to try to integrate these into the built environment. So we have integrated rooftop enclosures now, as well as other type of solutions here. But the common problem with all of these was that low frequency performance. We still had an issue with that. So what we created here at Sonobex is the Noise Trap Ace, which is our heat pump enclosure, which uses our Noise Trap Blocks product to allow passive ventilation and low frequency noise attenuation for heat pumps. And it works on a combination of three clear principles. So we have metamaterial based noise cancellation, and that is in the ventilation aspect of it. But for security and maintenance aspect, the remainder of the enclosure is constructed out of standard acoustic materials. So sheet steel with mineral wool to mitigate the other higher frequency. This solution is actually much better at low frequency performance. It's a modular enclosure, so we can actually now service different size heat pumps, different power ratings, and different types of chiller units. And we've fully tested this environmental chambers, and there is negligible impact on the machine's efficiency, and that's due to the airflow properties created through our metamaterial. Here's just some nice pictures of going through the prototyping phase. So 3D printing is very beneficial to prototype, test early stage acoustic metamaterials. But like I mentioned, we've fully moved to an injection molded solution now, which you can build enclosures, screens, and barriers out of. And to put this in perspective, the dark blue on the chart here is actually the noise trap ACE, which shows significant low frequency performance over our other standard louvered product, which actually amplifies the noise at low frequencies. This has been fully tested independent by third parties, and we can share those results if people need to look at those. But like I say, it's a much large improvement at low frequencies. We can actually now predict the real world performance, what you'd get on a standard type of heat pump. And why we was limited in the terms of the performance at low frequency as well is due to the fact of the roof on top of this enclosure was made out of standard materials. So that was a weak spot there. And I'll just end to show you some of the real world installations here. So this is actually the full noise trap ACE enclosure being installed around heat pumps. Like I mentioned, not affecting airflow, but mitigating that low frequency noise and removing any noise complaints from your neighbours here. And I will summarize with some take home points. So we can provide low frequency attenuation with natural ventilation. There's a lot of applications for that, but we're really focused on the heat pump market, which is growing. But our noise trap block solution is completely modular, lightweight, liftable by hand, which enables flexible designs. That also enables us to be installed faster on site, which obviously saves costs in the long run as well. And this was a picture of our most latest installation of a heat pump unit, which is, using our noise trap ACE, again, completely mitigating the low frequency performance, which comes from the compressor inside that heat pump. And that takes me to the end of my talk, and I'll be happy to answer the questions after the following talks.
Brilliant, thank you, Daniel. Moving outside and to big scale now, I'd like to introduce Gennaro Sica from HS2, who's going to tell us something about the work that they've been doing on noise reduction in relation to that massive program. Thank you, Gennaro.
Yeah, thank you for having me. I'm Gennaro Sica, and I am a senior acoustic engineer in HS2, and I'm leading a big part of the acoustic engineering in HS2 as part of the system integration team. Bear with me a moment for sharing the presentation. What I'm gonna go through today is really try to put some of the good work that I think Daniel and Gianluca are doing, and I think the rest of the material industry, a bit more within the context of an infrastructure project, and to see which could be, the opportunity where metamaterials can be used. So, of course, I'm gonna give an overview of the HS2, then just a quick glance about which kind of noise sources we have on HS2, and then try to go through acoustic challenge, which they are not just, I guess, for HS2, but generally for any big infrastructure project. So this is HS2 is the company that is promoting and building the new high-speed rail in Britain. The project is quite big and has been, going on for I think more than 10 years now. I joined 8 years ago when we just deposit the phase 1 bill. Now HS2 phase 1, which is the line in blue on this graph, is in construction. Then we have HS2 phase 2A, which is basically the bits of the railway which is linking the West Midlands to Crewe. And this one it has been it's really moving towards the delivery. And then we have like the phase 2B Western leg, which we just deposited the hybrid bill a few weeks ago. So this for giving you a feeling of the scale of the project, but also that there is quite a big opportunity here to improve the method for controlling noise and vibration. Then when we talk about HS2, I think and the source of noise on the scheme, I think HS2 is not just about railway noise. Of course, we have operational noise in overroute, which is given by the railway and any altered road and rail generated by the scheme. Also, we have also a big amount of stationary system noise, which are basically noise coming from mechanical or electrical kind of equipment, which can be a vent shaft, transformer, cabinets, or other plant. Also, we have HS2 Go also station and building for which we need to deliver acoustic comfort to passenger and staff. And the same, of course, we have also train where interior noise needs to be controlled in order to deliver a good passenger experience. And then, of course, we also ground-borne noise and vibration generated by the railway. And also we also have different kind of noise, which they go from a broadband kind of content to a tonal one. And we know at the moment, I think there is, of course, the metamaterial that we are at the moment in the market, they tackle more than tonal kind of frequency, but I know that the industry is also working hard in order to develop something which work for a large band of frequency. So let's go through some of the challenge which we could where we could see application of metamaterial. Of course, we have stationary system noise, which is a noise which is generally tonal or narrowband. It's generated by mechanical or electrical interaction. As pointed out by Daniel before, low frequency is very difficult to mitigate, and it's also something that is annoying residents. Also, we need to consider a lot of non-acoustic constraints, like, for example, the need to provide ventilation, and also the level and nature of sound produced might depend on by the source, which could be, like we said, a transformer or a ventilation shaft, or for example, a chiller on the top of a station. So if we go through, for example, the challenge that we could foresee, for example, for an infrastructure project. For example, there is like a common example of having a rail system compound, which is like a compound where we generally include like transformer or cabinet, and these need to be very close to the residents, and it is not enough to mitigate the noise level at the source. So, for example, like showed before, we need to provide an enclosure in order to mitigate noise. At the same time, to provide noise attenuation. And of course, the mitigation generally, they have a minimum design life of 30 years, while, sometimes asset can have a design life of a maximum 120 years. So, for example, in this case, of course, the challenge for the industry should be to have a material which got an high acoustic performance in comparison with the state-of-the-art, but without compromising all the other requirements. This is gonna be a common theme in my presentation, because of course a material needs to fit several tick boxes in order to be used on an infrastructure. And then, of course, to develop a solution which provides attenuation, ventilation solution, and of course, to have a material which got a greater life than the 30 years, and maybe also going towards zero maintenance. So, a similar, case or a similar, scenario could be the one where we have a vent shaft, which is very close to the residence, where, for example, again, we cannot mitigate the noise completely at source. And so, for example, we need to provide, for example, higher attenuation at low frequency. So, for example, one option could be, if this one is the vent shaft, this red kind of object in this top of the picture, top of the slide, we might decide, for example, to provide some lining within the shaft of the ventilation system in order to improve the low frequency. Of course, even in this case, there are a lot of non-acoustic constraints. And again, challenge for the industry is to have a material which doesn't just not perform well from an acoustic point of view, but also from all the other conflicting requirements. And in this case, of course, to have something that work, very well low frequency. And of course, always to try to extend the design life of the project, of the material, and also try to have a material which got minimum of zero maintenance. Then, for example, another, for example, example that I think could be quite interesting is like the ventilation, which the ventilation system, which are generally like this big vent, this big fan, which they can be in these two types. This is an axial fan, and this is a jet fan. Generally, for attenuating the noise at the source for this fan, we need to have like multiple attenuators, and sometimes these are very big, and sometimes also very difficult to maintain. Because especially when for example, after you grind your train in a tunnel, use the fan for extracting the material, but then all the material is sticked onto the attenuator. So again, in this case, of course, the challenge will be to have a material which reduces the space while keeping or improving the acoustic performance. So something which is smaller and perform in an equal or in a better way. And of course, you know, in this case, it's quite critical to have a better going towards a minimum of zero maintenance approach. Then, of course, we don't have also just challenge for stationary system noise. We also talked about acoustic comfort. For example, one, you know, of the issue that you have seen in literature is that, for example, when you have a train, you know, running within a tunnel, high speed, there is an increase in interior noise. And generally, this increase is 60 dB, which is quite a lot, considering that the loudness double each, there is a loudness increase each 3 dB. So in this case, the issue or the challenge that we have is to have a material which reduces interior noise, but balancing the train mass, because of course, even like Gianluca said in his previous talk, mass plays a big role in attenuating the noise. Of course, we cannot put a lot on material with a lot on mass on the train, because this one is going to have an effect on, for example, the energy performance of the train. So again, the challenge will be to produce a lighter material for keeping or improving acoustic performance, but without having a knock-on effect on our on other requirement. Then, of course, we have operational noise in overroute, which is a broadband noise. The noise sources increase with the speed, and we know that above 300 km/h, aerodynamic noise become relevant, while rolling noise is still present. So the aerodynamic noise is generally the noise generated by the top of the train, and for example, from the body of the train. So from source 1, 2, and 4 in my picture of the train, while, you know, rolling noise is generally source number 5, and is the source which consider the noise generated by the wheel rail interaction. And basically, from the graph on here, we can see that each source got a different spectral characteristic. And since the source are positioning in different part of the train, this might lead to have a more intelligent way of designing noise barrier, consider like the presence and the position of the source. So here there is a challenge which is related to the civil mitigation design, which are basically not just noise barrier, but earthwork, retaining wall, cladding, tunnel portal. And here again, the challenge is always to maximize barriers performance while, of course, minimizing visual impact, because, of course, no one likes to have like a very tall barrier in front of his house. And of course, another challenge is, you know, to push the minimum design life of the material in order to match the design life of the asset. Generally, most of these infrastructure assets, they have a maximum design life of 120 years. So in this case, the challenge for the industry should is to have system which got a better efficiency at speed greater than 300 km per hour. Also try to design a material in function of the source feature of the location. And then of course having something that is greater than 30 years and going towards zero maintenance. Then the last but not least of the issue or of the challenge that a big infrastructure project might have is like noise insulation at receptor location, which generally noise insulation is offered as a last resort for mitigating significant effect from construction of operation of the railway or any other infrastructure. And of course, sometimes we need to provide the ventilation system for ensuring that air circulation is provided within the property, especially when the windows is closed. So in this case, already seen by the work done by Gianluca and also by in a certain extent by Daniel, of course, develop material which go an acoustic insulation performance while providing natural ventilation is something that could be a good improvement, and of course throwing also into the mix the element of transparency, so to have like a windows which basically insulate noise but allow to have a natural ventilation. And this is the end of my presentation.
Many thanks, Gennaro. So finally, I'll hand over to our last speaker, who is Themos Kallos from Metamaterials.
Hello. Give me a minute to pull up my slides. So I'm Chief Science Officer for Metamaterials. So we're a publicly listed company in NASDAQ, and my role is to oversee the R&D programs in the company. Today I'm going to present a particular technology and application that is applied to buildings and indoor environments, but unlike the other speakers, is on the electromagnetic waves, not on the acoustic and sound waves. However, the application area...
Sorry, Themos, to interrupt. Your microphone is crackling quite a lot. I don't know if is it touching on your clothes or...
Yeah, let me reset one moment. Is it better now?
Yeah, that's perfect. Thank you.
Okay, sorry. This wireless technology is not very good. That's why we're trying to improve it. Okay. We are a publicly listed company, so I have to explain that this presentation will include some forward-looking statements, and but the actual results may vary, beyond what you see here. So the outline of my talk, I'm going to talk about the company and our applications first, and I'm going to focus specifically to how to improve wireless communications with a technology field we're developing called NanoWeb. And I'm going to present solution to that and then how we manufacture it at scale. Our inspiration when we started the company was from Richard Feynman, who in 1959 gave a famous talk about nanotechnology, and he said that at the time he couldn't see what exactly would happen, but when we would have some control of arrangement of things in a small scale, we'll get a much greater range of possible properties that the substances can have. And even though this was made over 60 years ago, it encapsulates what metamaterials are currently doing, which allows us to control things in the small scale. Our company was founded 10 years ago in London, in the UK, and last year we were listed in NASDAQ, and we are the first metamaterial company to do that, and we're at the stage where we are churning out different applications, not all of them using metamaterials. There's a lot of nanotechnology, nanostructure work going, but a lot of them are. Our headquarters are in Halifax on the eastern seaboard of Canada, and we also have facilities in California, 2 more manufacturing locations in Canada, also locations in Europe and Japan, where we work with local partners to further develop, distribute our products. In an essence, I like to present us as the Sherlock Holmes of light. So if there is some unusual problem that you cannot solve in the optics or radio waves, that's where we come in to provide the solution. That's when customers come to us. And in addition to this, we're heavily focused on manufacturing. So we are trying to fabricate metamaterials at scale. And as the humans have done this before twice relatively recently, one with the industrial revolution in the 1900s, where for the first time people started building stuff at scale and build the machines to build the stuff. And also in the electronic space with silicon and transistors, we went from discrete few number of transistors to having tens of billions of transistors in a very small area now. And this took decades in its case to get to a point where you can make these things cheaply and very efficiently. And that's what we are trying to do with metamaterials. I'll go briefly through some example applications that we've been working on. We started our first product in 2019, still on sale on our website, is laser protection eyewear. This is targeted for the aviation industry and pilots. It uses holographic films in order to reflect a particular wavelength of green laser light that is used for laser attacks against aircraft with laser pointers. We also have biosensing metamaterials. The idea here is that there's a thin film, you place it against the skin and acts like anti-reflection coating for the skin, but for medical radio wave applications, so it would allow more energy through the skin. We're also active in the plasmonic space on the security. So security features, these nice colorful patterns you see sometimes in banknotes. If you got your hands on a Eurocup ticket that took place last summer, it had one of our patterns on it, the actual physical ticket. And this is done using lithography techniques to print on these materials. We also have activity in transparent conductors. We're good at making transparent antennas, from design to fabricating them, and indoor television 5G antennas we can make with transparent conductive materials. Now, the application I wanted to talk more today was related to buildings and how we can enhance the coverage of 5G signals. You may be aware that the 5G use higher frequencies in the millimeter waves, around 26 to 28 gigahertz, and because of that they have smaller range and the reception is poorer compared to lower frequency signals. So the idea here is make a transparent film that can redirect, filter, redistribute the energy in places where you would otherwise would have no reception. And you want to place these films, for example, on windows or in the buildings, and they need to be transparent so that they are visually not present. They blend into the background. This is a much simpler solution than installing new bulky base station antennas with electronics. This can also be done for indoor environments. You can redirect the energy inside in order by placing this film on the window. I have a little video here to show you. So this shows from our partners Sekisui in Japan a concept of how this would work. I'll let the video play, but basically we assume an antenna on the outside and then different films that installed in various areas indoors to redistribute the energy in places where you would otherwise get little to no reception. So that's the vision where we're trying to get. This is especially important with smart buildings that are filled with different sensors, IoT devices, and so on, so that there is seamless connectivity in all of them. The technology we use to achieve that is the nanoweb metal mesh. So we are basically printing very thin metallic wires. These are very small, less than 1 micron, about 500 nanometers. So they're invisible to the human eye, and we can make them in a mesh pattern in the simplest solution. So that creates a conducting material that is visually transparent. Here you can see some electron microscope photos of how it looks, the material. There are other materials that do similar function. ITO is the most common one that is currently used in most mobile phones. There are also like silver flakes and other types of nanowires. The difference with nanoweb is that we have much more control and we can imprint metamaterial designs beyond what a simple mesh. So this is something that you do not have control of in other chemical solutions and random wires. And because of that, we have a material that can have a higher transparency for the given conductivity. Now we take that and we design it in order to perform a certain function to redirect the electromagnetic energy. So basically, we can implement, for example, a mirror array using this transparent metamaterial. In geometric optics, you might have like a shape like this on the left-hand side. So we're mimicking that shape by using a completely flat metamaterial pattern, a reflect array. One way to design this is to use an shell type grating. So the grating, these types of gratings are well known in optics, and they can disperse and reflect the energy in anomalous angles. So we're basically implementing this type of function, but with these metallic patches of nanoweb. And I'll show you a simulation here provided by our partners at Sekisui. So on the left-hand side, you have 2 corridors that meet at 90-degree angles, and there is a transmitter on the left-hand side. Right at the junction, you place the nanoweb material to reflect and redirect the energy on the room and the back. And you see the simulation results on the right-hand side at 2 different frequencies, 3.75 and 60 gigahertz. So the top row is without any reflector, where you get poor reception at the edge of the room at the back. But if you add this reflecting film, then you get much better reception, much more signal at the back. And this is also dispersing the signal, so it can also expand the beam, not just reflect it. I want to show you here some simple fabrication results. So in a little demo setup, we have 2 antennas and 2 films at different angles. And what is shown is that there is an incident signal coming from minus 20-degree angles over here on the left. Normally, you would expect to get a signal at plus 20 degrees, so that's the reference here. By putting the nanoweb metasurface, you were able to redirect that to more than 40 degrees higher. So it doesn't act like a mirror. And the key point is that you can basically make different films for different angles and redirect the energy as needed. I'll close off by explaining how we manufacture that, because a lot of this stuff can be done with e-beam tools, but we've actually invested a lot of effort to be able to do this faster and cheaper. So we are focusing our effort on films that have small feature sizes in large volumes and at low cost. There are a couple of ways to fabricate these things. First one is, what I call the interstellar methods. You can take an e-beam tool, send it in orbit around Earth, and if it goes fast enough due to time dilation, when you come back, much less time would have passed on Earth, and then you are able to have these things on time. However, this is not as realistic. Instead, we've using a method called rolling mask lithography, that basically the pattern of the film is on this cylindrical mask that then is exposed over a photosensitive material. And this allows us to do a roll-to-roll fabrication of these films. These are some of the patterns that can be made with this technique. So we can do, different kinds of features, including the nanoweb and reflector type elements that are interesting to this application. We currently are setting up this year a roll-to-roll rolling mask lithography tool in our California facility. So these are the main steps. We start with the rolls, you exposure with the light. Then there is a baking process step. Then is being developed. Then we deposit the metal to create the layers. And then there is a lift-off and protection integration. All this was done in a small scale, and now we're building the capability to do this in rolls at a time. A sister manufacturing technology we use for the same is in our Canadian facility. This is nano imprint lithography technology. Is complementary technology to the rolling mask I explained before, but is also used to fabricate roll-to-roll structures of this with nano size features at a large volume. So we're aiming around 7 million square meters per year capacity in order to address this and other needs of functional films. And that concludes my talk. Thank you very much for your attention, and I'm open for questions.
Many thanks, Themos. So, yeah, thank you, speakers. I mean, a real range of types of material as well as applications, and also a really good insight to where some of these are in relation to, I guess, industrial take-up. We've got some questions that have come specifically around the presentations. So I think we'll deal with those first and then maybe open up the discussion first. So to Gianluca, there was a question. Why would you use a 1mm hardboard as a reference instead of a standard soundproof wall like the ones used in cubicles, which are the standard acoustic foam panels or soft material sound curtains?
So I used an artboard panel because I wanted something which weighted the same, and the message I wanted to show the effect of the geometry over the mass of the panel. Regarding the foams or the tents, I can answer on the tents, for instance, because that is a comparison we have done, and the tents typically go up to 9 dBs when mounted. And these are the acoustic tents, so like the ones that, so IKEA started selling some during the lockdown. They go up to 6-7 dBs, and you have to consider that anyway the sound goes through, so it's a direct block, but there are a lot of leakage. And if you are asking about those instead, typically the effect of those is at high frequencies, while the noise that we wanted to work on was mainly, so we wanted to block the peak, remember? We wanted to make something tailored and also something that worked at frequencies which were not necessarily high or medium high. Anyway, that's a very good suggestion, so I'll do that next time.
Thank you. And then as a second question for Daniel, how do you prevent insects, small mammals, etc., taking up residence inside the noise blocks?
It's a very good question, and it's something we have thought about. So integrating in our injection mold process, we have a section where we can apply a standard insect mesh or bird mesh actually on the front of the noise trap blocks, and that doesn't impact the airflow properties of that. So yeah, very sensible question, but it's something that's integrated into the design. And yet we called it internally a bird box for a while because of that issue, but we have resolved that and have the solution now.
Great, thanks, Daniel. And then there's a couple of questions for Themos. The first is, by using your passive 5G metamaterial reflector, how many base station antennas would you be able to reduce from the total system, e.g. one each X meter or other measure?
Yeah, so if we're talking outdoors, then it's probably half to 1/3 of what you would require. I mean, this obviously depends on a lot of things like the environment, the coverage, and so on, but that's a starting point. For indoor coverage, I mean, is infinite because you wouldn't be able to place any antenna there. So it's either you got no coverage or you just cannot use 5G. You have to rely on Wi-Fi or older, slower communication methods.
Okay, thank you. And then the second question, what is the benefit of making a 5G reflector that is transparent? Is it only about the aesthetics?
Yeah, well, one is aesthetics, because you want to install these things, they work best when they cover large surface areas. So you could put like a huge metal sheet there, but it would look weird, and many people don't like it. We will actually talk to many city planners and they tell us, that they don't want any more antennas in their trees, or they try to cover them up, blend them in the environment. So this solves the problem. There's also a functional reason that has to do with the indoors, that the best reception is through the window. So if you put something that's not transparent there, you're just blocking the view. And if you think maybe on not in building that, but automotive maybe, or other areas where it's actually useful to see outside, then having something transparent is the only solution there. And the partnership we have with Sekisui, the feed manufacturer, is to eventually release this with a telecom provider in Japan into people's houses.
Okay, thank you. There's a question here to Gennaro. How much do you think that the expected noise increase impacts the public perception of HS2? And the questioner said, they asked because in airports, this is a crucial factor for new builds, while for a lot of time, rail was expected to be predictable.
I think it's generally one of the challenge of high-speed transportation, because I think it's one of the, let's say, few I think concern left on the noise and how this one is basically perceived by the public. So I cannot give you a number because but for sure it plays quite a lot. It plays quite a lot of big role in this, such that, for example, sometimes during, for example, consultation for for example, the phase 2B, maybe like in phase 1, we generally do we generally do some sound demonstration which basically gives to the people to give them an idea of how HS2 will sound within their context. For example, this is a technique which is called auralization. For example, lately there has been also quite a huge, project within, for example, Shift to Rail, in order to standardize this, in order, to manage, let's say, this, what, Gianluca was asking, to manage, the perception of a new railway within your within your environment or behind your backyard, something like this.
Okay, thank you. There's a question here. With the fixation on passive ventilation, do we not get better impact using low energy mechanical ventilation systems? Maybe, I'm not sure who wants to pick that up.
I can, talk about that, Deborah.
Yep.
So from our experience, mechanical ventilation just complicates things. So obviously you have to power a fan system, you need the control system, ventilation control system there. So in short, there's more things to go wrong, and you obviously have to maintain sort of a mechanical ventilation system, and then you have the operational cost of running that as well. But yeah, you would get better airflow provided through that, but it also increases the noise levels because you're putting a mechanical fan into that system, which then you add more noise due to the fan because of that. So yeah, it's correct in saying, you could use a low energy mechanical system, but we found in the market people prefer a passive solution because it's more simpler, less things to go wrong.
Right, thank you.
And as you were saying, less things to maintain over time, yes.
Right, okay, thank you. And one final question for Meta. Is the 5G indoor coverage enhancement bi-directional, i.e. does it help get signals out as well as in?
Yeah, in general, this, what I showed is, yes, symmetric systems, yes, but usually they would be operated in one way, like the high power transmitter will be on one side, but in principle, it could work two ways, yes.
Okay, thank you. Right, that's all the specific questions that have come through from the hub, but I've got some more general ones which I'm interested to sort of pose to you. So maybe Gianluca, you could pick this up first. One of the things that I guess with all of this is what is the status of understanding of the materials and the data use, particularly by product designers, architects, interior designers, to be able to actually fully appreciate the benefits and then take that risk in terms of specification. Where are things for you at the moment?
For us, so we have two levels. The first is whenever we have an architect coming and testing the materials, they immediately go away full of the sky's the limit, they say, because the effect is easy to feel, right? You immediately see the effect, hear the effect, and you immediately can compare it with other materials. While in terms of standardization of techniques to characterize the materials and give a number, so for instance, I've been asked before, why don't I use foams? Because foams have all sorts of standards, uncommon. Well, I found data sheets of foams which are completely different in terms of the number that they use. And so it's very difficult to make a standard comparison about effects. And if some of the standards don't work for the metamaterials we do, this is a bit more complicated. So the answer is, when I talk, so there is a qualitative appreciation, which is extremely high, but there is clearly a block on the way in putting in a quotation and a numerical quotation for a decision maker, that if we cannot overcome, this obviously slows us down.
Yeah. Anybody else want to comment on that if they've got maybe a different position or not a problem. I'll move on, actually extend a little bit on that, because I'm also interested in, particularly maybe Daniel, in how much engagement and interaction do you have to have with others in the supply chain when in delivering your product, again, to get effective use. You know, are you starting to move towards a thing where a number of suppliers are providing a whole package to get the maximum, or where do you think the supply chain development will go in the future?
Yeah, we have had quite a lot of engagement. We've had to do a big education process of explaining how these technologies work. In short, they still work the same, but much better. So it reduces noise at the end of the day. One thing we have faced is in terms of specification and specifiers. So our acoustic materials, Metamaterials, we have a range of acoustic panels which have no mineral wool inside. But in a lot of specification and request for quotations, it still asks for a certain density of Rockwool to be included inside an acoustic panel. So there's a big process of educating the market, showing people what's out there. It's taken a long time to get those real world case studies, which then obviously proves themselves when you can physically measure the difference, reduce the number of noise complaints, for example. Manufacturing techniques, we started with 3D printing, but trying to develop engineer for real world applications is one of the key things that we've had to go through, and we've had a lot of support through that process to date.
Brilliant, thank you. I guess and again another extension of that is where are the clients in I guess specifying particular performance and indeed standards and certification requirements that will actually help with the uptake of metamaterials? Is there still a gap there, which again requires some addressing so that, you know, really they can come to the fore? Maybe Themos wants to say something about that.
Yeah, I can comment on that. I mean, in many cases, there's new materials for old applications, and there are already standards in place that we need to adhere to. So by inserting a new material, we basically have to re-verify the whole stack, the whole application against these standards. And that's something that's usually the burden is on the material designer, manufacturer to do. So often we talk to customers and they say, okay, you know, we need this is a new material, but how do we know it will last, you know, 5 years or 10 years, whatever. So it's important to have this data in place, and is actually required before you can have a real product out of it. Obviously, it depends on the application area, like, you know, aerospace, automotive, you know, they have different requirements.
Yeah, thank you. I mean, actually, I want to come back to Gennaro there, because I was interested in how much of a driver was the opportunity that you brought to, I guess, the HS2 Limited in meeting not just the, you know, the sort of laid out requirements, engineering requirements, but to demonstrate, you know, to government what a step up they were also driving for in terms of things like noise reduction. And from your position as a sort of specialist in the supply of that, how much did you drive those expectations, ambitions in terms of noise reduction over and above what's actually required by regulation?
Yeah, I guess that, you know, HS2 is a transformative project in a lot of kind of aspect, and of course also the acoustic aspect is something that we try always to push, because you know, having material that they perform, you know, better means also, you know, having, you know, more confidence in the, you know, in the infrastructure and the industry in order, you know, to tackle this problem about, you know, noise. So and we are generally very up to this challenge. Might be because of my background, but we always try to push it and to see if there are opportunity for application of this technology, because at the end of the day, the railway environment, as any other infrastructure environment, the material itself needs to fit several boxes, and it's not just having a material which perform acoustically well, but need to work. There are also other requirements that they need to fit, and this is where like application in the real world and result in the real world that we can move these things forward. And HS2, like any other big infrastructure project in the world or just in UK, they can provide this opportunity, especially for us, which we have like different phases. So if something might be not be ready for phase one, we might still think to have improvement for other phases of the project, and we will still deliver some good noise reduction for the public.
Yeah, great, thank you. And I want to go back to Gianluca now and ask, where is the global position for you? Is that critical to get the scale of application to drive development of more materials? And where does the UK fit in that? Are we a trailblazer? Are we a catcher-upper, for want of a better description? Where do you think we sit?
So of the maybe 6 acoustic metamaterials or company in the world, 3 are in the UK. Yeah, okay. And that answers the first question. And I think it has been recognized early that metamaterials are an opportunity, a great opportunity for us as a country. And I think the position we want to have as a country in the world is also underpinned by the possibility of having technologies which are groundbreaking like that up our sleeves. Yeah. So, so at the moment we have customers in Italy, customers in the Netherlands, customers in Turkey also in some cases. We see that there is an appetite growing for materials, because until probably 2 years ago they were sci-fi, and now we're starting to see applications. Daniel was saying it was difficult to get to the case studies that people would believe to, instead of asking Rockwool all the time. But we're getting there. People are starting. We moved from the visionaries, let me call it that way, to the people who are starting actually to understand the opportunity, and the fact that Gennaro was mentioning that as a possibility for a transformative project like HS2 is an important bit. So there is a push for this. There is also a push from us as a UK in developing this technology. I hope I answered your question, Deborah.
Yeah, no, that's great. It's great. And I know it's a very generic question to something that's very complex. Just 1 minute left. Daniel, I mean, I was just interested in the sort of journey of your company, really coming out of a university in the UK, and then now actually being part of a much larger organization. Where do you see the global stage in maybe drawing out the real value for metamaterials?
With us, it was all finding the right applications, and the results sell themselves effectively. If you can provide a lower cost, better performance solution that's lighter and thinner, for example, it's not an easy sell, but it makes it a lot easier to go through that process. But yeah, like Gianluca just said as well, we're getting multiple inquiries across Europe and wider afield to sort of try get these technologies working now. We do have repeat customers as well. So yeah, the case studies we've got out in the real world we can use those results as a good benchmark, and we actually know what it is doing. It does sound too good to be true in a lot of cases. So when you can prove it in real world test data, then it sort of, like I say, sells itself on the back of that.
Perfect, thank you. Right, well, we're right up to time now, so it just remains with me. Thank you very much for the speakers. It was a really interesting session, and that I really appreciate all the effort. And also thank you for the audience out there. I hope you really enjoyed it. Good afternoon.
Thank you.